Hey everyone, welcome back to the channel. Today, we're diving deep into one of the most critical aspects of training neural networks, hyperparameter tuning. We'll be covering learning rate selection, batch size optimization, training steps, and the powerful world of learning rate schedulers, including warm-up strategies and gradient clipping. By the end of this video, you'll have a solid understanding of how to choose these hyperparameters to get the best performance from your models. So let's get started. Before we dive into specifics, let's quickly understand what hyperparameters actually are. Hyperparameters are configuration settings that you define before training begins. Unlike model parameters like weights and biases that the model learns during training, hyperparameters control how the learning happens. Think of it this way. If your neural network is a car, the model parameters are the car learning how to drive, while hyperparameters are settings like the speed limit, acceleration rate, and braking distance you set beforehand. Today, we're focusing on the most impactful ones: learning rate, batch size, training steps, and schedulers. Let's start with the learning rate, arguably the single most important hyperparameter. The learning rate controls how big a step your optimizer takes when updating model weights. It's typically denoted as LR, or alpha in code. Imagine you're hiking down a mountain in fog, trying to reach the lowest valley. A high learning rate means you take huge steps. You'll descend quickly, but might overshoot the valley or even jump to the wrong side of the mountain. A low learning rate means tiny steps. You'll carefully descend, but it might take forever, and you could get stuck in a small dip that's not actually the lowest point. The sweet spot, though, that's what we're trying to find. So, what values should you actually use? Here are typical starting points based on model architecture and optimizer. For Adam optimizer with transformers, start around 5e-5 to 3e-4. That's 0.00005 to 0.0003. For SGD with momentum on CNNs, try 0.01 to 0.1, much higher than Adam. For Adam W, the popular choice for large language models, 1e-4 to 1e-3 works well. But remember, these are just starting points. The optimal learning rate depends on your specific dataset, model size, and batch size. Now, here's a pro tip. Don't just guess your learning rate. Use a learning rate finder. This technique, popularized by Leslie Smith, helps you automatically discover a good learning rate range. The idea is simple. Start with a very small learning rate, train for a few batches while exponentially increasing the learning rate, and plot the loss. The optimal learning rate is usually where the loss decreases most steeply, just before it starts to explode. Here's a simple implementation using PyTorch. We're exponentially increasing the learning rate from 1e-7 to 1, tracking the loss at each step. The matplotlib plot will show you exactly where your sweet spot is. Now let's talk about batch size, another critical hyperparameter that's closely related to learning rate. Batch size is the number of training examples your model processes before updating its weights. You have three main approaches. Stochastic gradient descent uses a batch size of 1, updating after every single example. This is noisy, but can escape local minima. Mini-batch gradient descent uses batches between 16 and 512 examples. This is the most common approach, balancing speed and stability. Full batch gradient descent uses your entire dataset. This is stable, but computationally expensive and rarely used. Like everything in machine learning, batch size involves trade-offs. Small batches, say 16 or 32, give you more frequent weight updates, better regularization through noise, and fit in smaller GPU memory, but training is slower and gradients are noisier. Large batches, 256, 512, or even higher, maximize GPU utilization, stable gradients, and train faster per epoch, but they need more memory, might generalize worse, and require careful learning rate scaling. Here's the rule of thumb. When you double the batch size, you should consider increasing the learning rate by roughly the square root of 2, which is about 1.4 times. This is called the learning rate scaling rule. Let's see how this looks in code. Here, we're setting up a data loader in PyTorch with a batch size of 64 and 4 worker processes for faster data loading. Notice we're also shuffling the training data. This is important for preventing the model from learning the order of examples. For modern GPUs with lots of memory, start with a batch size of 32 or 64, then increase it as much as your GPU memory allows, but watch your validation performance to make sure larger batches aren't hurting generalization.
Now let's clear up some terminology. Training steps versus epochs. An epoch is one complete pass through your entire training dataset. If you have 10,000 examples, one epoch means the model has seen all 10,000 once. A training step or iteration is one weight update, one forward pass, and one backward pass on a single batch. Here's how they relate. Steps per epoch equals your dataset size divided by batch size. So with 10,000 examples and a batch size of 100, you'll have 100 steps per epoch. And total training steps equals epochs times steps per epoch. So how long should you train? For fine-tuning pre-trained models like BERT or GPT, 3 to 10 epochs is usually sufficient. More than that, and you risk overfitting. For training from scratch on small datasets, think CFAR 10 or MNIST, 50 to 200 epochs is common. For large-scale pre-training, we're talking hundreds of thousands to millions of steps. But here's the thing. You should always use early stopping based on validation loss. Stop when your validation loss stops improving for several epochs, even if you haven't hit your target number of epochs. This prevents overfitting and saves compute time. All right, now we're getting to the really powerful stuff, learning rate schedulers. A learning rate scheduler automatically adjusts your learning rate during training. Why? Because the optimal learning rate changes as training progresses. Remember our mountain hiking analogy? At the start, you want big steps to quickly get down the mountain, but as you approach the valley, you want smaller, more careful steps to precisely reach the lowest point. Schedulers help you start with a high learning rate for fast initial convergence, then gradually reduce it for fine-grained optimization near the end. This almost always improves final model performance. The Cosine scheduler is one of the most popular and effective schedulers, especially for transformers. It follows a cosine curve, smoothly decreasing the learning rate from your initial value down to nearly 0 by the end of training. The formula looks like this, and don't worry, libraries like PyTorch implement this for you. Why is cosine so good? First, it's smooth, no sudden jumps that could destabilize training. Second, it has a nice property. The learning rate decreases slowly at first, then faster in the middle, then very slowly at the end. This gives your model time to fine-tune as it approaches convergence. Cosine scheduling works great for most deep learning tasks, especially vision transformers and language models. The linear scheduler is simpler. It just linearly decreases the learning rate from the initial value to 0. Unlike cosine, which has that smooth curve, linear decay is constant, the same amount of decay at every step. Linear schedulers are popular in NLP, particularly for fine-tuning BERT and other transformer models. They're simple, predictable, and work surprisingly well for many tasks. In practice, cosine often performs slightly better than linear, but the difference is usually small. I'd recommend trying cosine first, but don't be afraid to experiment with linear. Let's see how to implement these schedulers in PyTorch. For cosine annealing, we use cosine annealing LR. You specify the optimizer, Tmax, which is your total training steps, and eta min, the minimum learning rate, usually 0. For linear decay, we use linear LR. You can specify start factor and end factor to control the decay. The crucial part is calling scheduler.step after each training step or epoch, depending on your schedule or configuration. Don't forget this, your learning rate won't change otherwise. Now, here's a technique that can make a huge difference: warm-up. When you start training, especially with large learning rates, the gradients can be unstable. Large initial updates can push your model into a bad region of the loss landscape. Warmup solves this by gradually increasing the learning rate from near zero to your target learning rate over the first few hundred or thousand steps. You can see on this graph, we start at a very low learning rate, linearly increase it during warm-up, then apply our main scheduler afterward. This simple trick stabilizes early training and often leads to better final performance, especially for large models. Let's implement warm-up with our schedulers. Here, we're using Get Linear Schedule with Warmup from the Transformers library. It's super convenient. We specify num warm-up steps, typically 5 to 10% of total training steps, and num training steps. In this example, with 10,000 total steps, we're using 500 warm-up steps. That's 5%. During the first 500 steps, the learning rate increases from 0 to our initial learning rate, then it decreases linearly for the remaining 9,500 steps. For transformers and large models, always use warmup. For smaller CNNs, it's less critical, but still often helps.
All right, let's talk about another crucial technique: gradient clipping. During training, especially with RNNs and transformers, you might encounter exploding gradients, where gradient values become astronomically large. When this happens, a single weight update can completely destroy your model's learned parameters. Your loss will suddenly jump to infinity or NaN, not a number. Gradient clipping prevents this by capping the magnitude of your gradients. If gradients exceed a threshold, we scale them down proportionally. This is now standard practice for most neural network training, especially for sequence models. The key parameter here is max grad norm, the maximum allowed gradient norm. Typical values range from 0.5 to 5.0, with 1.0 being a very common default. Here's what happens. Before each weight update, we calculate the total norm of all gradients across all parameters. If this norm exceeds max grad norm, we scale all gradients down by the same factor. The important thing is we scale all gradients together. This preserves the relative magnitudes and directions, just reducing the overall step size. Implementing gradient clipping is super easy, just one line. After computing gradients with loss.backward, we call torch.nn.util.clipGradNorm_. We pass in our model parameters and our max grad norm value. Here, it's 1.0. Notice the placement: after backward, but before optimizer.step. This is critical. We clip the gradients after they're computed, but before they're used to update weights. The function returns the total norm before clipping, which you can log to monitor if clipping is actually happening. If this value is frequently above your threshold, you might need to adjust your learning rate. Now, let's see how all these pieces fit together in a real training loop. We set up our optimizer with an initial learning rate, create a cosine scheduler with warmup, and define our max grad norm. In the training loop for each batch, we do the forward pass, compute loss, backward pass to get gradients, clip those gradients, update weights, and then step the scheduler. Notice the order: backward, clip, step optimizer, step scheduler. This sequence is crucial. We're also logging the current learning rate, super useful for debugging and understanding what's happening during training. So how do you actually find the best hyperparameters for your specific problem? First, start with established defaults from papers or repositories working on similar tasks. Don't reinvent the wheel. Second, tune one hyperparameter at a time. Start with learning rate, it has the biggest impact, then batch size, then scheduler settings. Third, use grid search or random search for systematic exploration. Random search often finds good configurations faster than exhaustive grid search. And finally, for larger projects, consider using tools like weights and biases sweeps or Optuna for automated hyperparameter optimization. Before we wrap up, let me share some common mistakes I see all the time.
Pitfall number 1, using the same learning rate for all parameter groups. For fine-tuning, use a smaller learning rate for pre-trained layers and higher for new layers. Number 2, forgetting to call scheduler.step. Your learning rate won't change, and you'll wonder why scheduling isn't working. Number 3, not using Warmup for large models. This can cause training instability and worse final performance. And number 4, setting max grad norm too low. If you clip too aggressively, you'll slow down learning. Start with 1.0 and adjust based on your gradient norm logs. Here's a quick reference for starting configurations based on common scenarios. For fine-tuning transformers, learning rate 3e-5, batch size 16 to 32, cosine scheduler with 10% warmup, and max grad norm 1.0. For training CNNs from scratch, learning rate 0.1 with SGD, batch size 64 to 128, cosine annealing, and max grad norm 5.0. For training transformers from scratch, learning rate 1e-4 with Adam W, batch size as large as your GPU allows, cosine with 5% warmup, and max grad norm 1.0. Remember, these are starting points. Always validate and adjust based on your specific results. All right, let's recap the key takeaways from today's video. Number 1, learning rate is your most important hyperparameter. Use a learning rate finder to discover good ranges. Number 2, batch size affects both training speed and generalization. Scale your learning rate when changing batch size. Number 3, use learning rate schedulers, especially cosine. They almost always improve performance. Number 4, Warmup stabilizes training for large models. Use 5 to 10% of total steps for warmup. And number 5, always use gradient clipping with RNNs and transformers. It prevents training crashes. If you want to dive deeper, here are some excellent resources. The original Learning Rate Finder paper by Leslie Smith, Cyclical Learning Rates for Training Neural Networks. The BERT paper, which popularized many of these techniques for transformers, and the Hugging Face Transformers documentation, fantastic practical guide with code examples. And that's it for today's deep dive into hyperparameter tuning. If you found this helpful, please hit that like button and subscribe for more deep learning tutorials. Drop a comment below with your biggest hyperparameter tuning challenge. I read every single one and love helping out. In the next video, we'll be exploring advanced optimization techniques, including learning rate schedules with restarts and discriminative learning rates. Thanks for watching, and I'll see you in the next one. Happy training!